Hello, everybody, and welcome to another lesson from our room 229 online. So here we are, we're talking grade 12 physics. This is unit 2, lesson 7. We're going to talk about gravitational potential energy. Before we start, I hope you're all doing well. Hope everything's okay. We're in week 2 of this quarantine nonsense. We're going into our third week off now in March, almost April. So I hope you're all well. Hope you're all staying sane. Not playing too many video games, but you got to do what you got to do. All right. So let's take our minds off some of this global pandemic nonsense and talk about some wonderful physicsness. Okay, physicsness. Is that a word? It is because I said so. All right. So gravity. We talked about potential gravitational potential energy last year, right? But in that sense, we talked about it from a constant gravitational field view, right? That the force of gravity is equal to mg, right? In our lab frame, g is constant. We know that that's not always the case. We know that in some cases, when we talk about, um, outside of our lab, outside of the Earth, away from the Earth, when r increases away from the radius of the Earth, that has to go down, right? Gravity is stronger on different planets and weaker on other planets. If you go to the moon, it's a sixth. So this is not a constant in the universe. It's a constant roughly around, a couple hundred kilometers around the Earth, but after that point, it gets weird, right? So last year we said, that work is equal to force times my displacement. So this will be mg, and then we called it h. And using the work energy theorem, we were able to say that this is u. Our potential energy was mgh. But now let's change our viewpoint to universal gravity, where the gravitational field changes as a function of 1 over r squared, an inverse square law. Remember why there's inverse squares? Why are there inverse squares? Remember? Spheres, radius of spheres, and all that sort of stuff. So let's say now we have a mass m, and it's on the surface of the Earth. Let's call that Re, capital Re. So that's the radius of the Earth. What is that? That's 6.38 times 10 to the 6 meters, right? And we're going to increase it to a new height. So it's going to be R2, which is the radius of the Earth, plus h. How much work do I have to do this? Like, think about a satellite. I want to take a satellite and launch it into one of these, let's say, geosynchronous orbits around the Earth, so I can have a GPS satellite out there. How much work do I have to do to get it up there? Right? And we know that it's going to be acted on by our gravitational field given by this universal gravity formula, right? GMM over r squared. And we also have our work equation here. I'm changing it slightly to say that the work done also, remember, the work done is also going to be equal to, we're going to call this my change in potential energy. Right? So that's how much potential energy I am increasing by increasing its height. Right? We can think about it as some sort of thing, and I'm going to take my mass, I'm going to bring it up to a new one, so I'm increasing its potential energy by some delta U or something like that. Okay? Okay, so where were we? Excuse me. So now, if I'm on the Earth here, I can think of my field as being a 1 over r squared like this. And I'm going from this was my r1, this is the radius of the Earth, to a new position, the radius of the Earth, plus some height h. And for me to determine the work, remember that's looking for the area under this curve. And that's going to be a complicated problem. Because areas under these curved lines is not straightforward. We can't just turn this into a geometrical property of triangles and squares like that. We have a function, right? We have this function here, and for us to actually determine this area underneath here, we need to do some calculus. Okay, so I'm going to spend a little time here doing a little calculus derivation of the formula for potential energy. There is another proof in our textbook. It's a strange one using some root means and things like that, which is kind of weird and non-intuitive. But For those of you who aren't in calculus and have no interest, just skip the next couple minutes and go straight to the formula. But I'm going to do just a quick little calculus introduction to integral calculus of calculating areas underneath curves. So otherwise, just skip over. So I'm going to rewrite my expression here for work. Instead of it being the typical right, work is force times displacement. Work is now, I'm going to express this slightly different. It's going to be what we call an integral of my function. I'm going to call it a function of r. Right, that's my gravity force as the force of gravity as a function of r multiplied by something called dr, and it's going to go from r1 up to r2. So what that statement says, this is an integral expression which says I'm going to take my this is f, I'm calling this now f of r as a function of r, and I'm going to break this guy up into little pieces. I'm going to call them dr. So I'm basically going to break this up in these little slivers, and I'm going to add all the slivers up. All right, so really I'm taking the sum of, if I call this delta x for now as a finite difference, it's the function as a there multiplied by the width there. So it's the sum of all this height as a function of r multiplied by the delta r, not x, okay? The finite difference here. But then if I make these slivers infinitesimally small, right? I go from a finite sum to what we call an integral or an infinite sum. And the pieces go from having a finite width of delta r to an infinitesimal width of dr. Okay? So when we do integral calculus like this, we're basically taking the limit as this delta r approaches 0. And that's what this dr really means. It's when these widths here, right? This height here is f of r, and it's basically a little box that I'm making right here. F of r multiplied by delta r. But if I go to an infinitesimal sum, which is this is the squiggly s. So this is a Greek s. This is a little squiggly s. This means an integral. And it's gonna, if I add up all those infinitesimally small boxes, infinitesimally thin boxes, I get the finite area underneath that whole thing. And that's what that means. And we have these indices, r1 and r2, that represent where we're integrating from. Okay, we're going from r1 to r2, and that's what it says. So this is a definite integral as opposed to an indefinite integral. Okay, so I'm going to replace now. I'm going to draw r1 up to r2, and my function, f of r is g m over r squared, Newton's gravitational law, dr. Okay, and I know that g, m, those are all constants, so they will all be factorable out of the sum. Remember, this represents a sum. If I add a whole bunch of things, they all have the same common factors in them. I can just take them out of the sum. So I'm just going to factor those out of my integral. Now I have 1 over r squared dr. So now you may be looking at this thinking, how the heck do I do this? I don't know integral calculus. I only know derivative calculus. What this is asking really is what function, when I take the derivative of it, gives me 1 over r squared. So what is the function? What expression, if I take the derivative of something, dr, of something, some unknown here, I want to get 1 over r squared. It's saying it's giving you the answer. The 1 over r squared is my answer. I need to find out what gives me that. And I know, so this is r to the negative 2. Using my power law, if I go negative 1 over r, that's the same as the derivative with respect to r of negative r minus 1. If I bring the negative 1 down, negative 1 times negative becomes positive. and I lose another one. -1 minus 1 is going to be -2. So this is my answer, really. Now the problem is I have these indices, so using what we call the fundamental theorem of calculus, which is, again, this is all way beyond this course, but I'm just going to show you the proof here. We have to go, okay, so we have to go -1 over r, that's my answer, and I'm going to evaluate this from r1 up to r2, which basically means GMM minus 1 over r2 take away -1 over r1. And this all works out nicely to show that the potential difference, my delta U, is going to be GMM, my constants. And if this is going to be negative times negative positive, so I'll put that one first. So 1 over r1 take away 1 over r2. And there's my expression for a change in potential energy from a position R1 to a new position R2 anywhere r distance away from mass of the Earth, right? If I take a little mass, this isn't ME, this is the mass of the Earth. If I take any mass and I move it away from Earth, I'm going to get this expression. Okay, so therefore the work required to move an object, M, from a position R1 to R2 of above a planet, any planet, moon, sun, sun's not a planet, whatever, any celestial object with mass m, and thus the change in potential energy, oh, I forgot a bracket, awful, is given by this expression. So my gravitational potential energy, mu, right, really this should be delta U, right, because it's all we'll talk about this later in the next unit lesson. Where's our reference point? We're only talking about now a change in potential energy, so I should put a delta there. Okay, we have our g, which is our gravitational constant. We have our mass m, our little m of the object, and our two radii, the initial and final radius. Okay, because, and I have to use the word radius because it's always spherically symmetric. Gravity is wonderful in that it's a spherically symmetric thing. As I go farther away, these all change with respect to r, not with respect to any sort of x or y coordinates. It's always just radially outwards. Okay, and that's my expression. Now, from here we can go a little bit farther. We can say, okay, so what happens if I want my R2 to be infinitely far away? What if I want to get completely far away from the Earth to the point where there is no more influence from the Earth's gravity? If I want to take an object, M, let's say, and I want to move it away from an object until it's so far away it doesn't feel anything anymore. We can call this an escape energy. How much energy is required for us to escape the gravitational field, gravitational pull of the Earth? In that case, we're going to take our R to basically infinity, because that's the point in which the field no longer counts, right? 1 over r squared is equal to 0 when r approaches infinity. Okay, so I can't really do this. This is kind of ugly. Okay, I really should be taking the limit as r2 approaches that, but really this whole term 1 over infinity, which is kind of gross, 1 over r2 as r2 approaches infinity. Let's say that way. We really should be doing this as the limit as r2 approaches infinity. We really should do that, but who cares? Whatever. This whole thing goes to 0, it vanishes, it's gone, and we end up with this expression to say that this much energy is required for me to take an object and throw it away from the Earth. That's how much energy I have to toss. Let's say I want a ball and I want to throw it up in the air so fast that it never comes back down. It's just gone forever. That's the amount of energy. Let's call this the escape energy. Okay? So the energy required to escape the pull of Earth's gravity is this big G constant, gravitational constant, 6.67 times 10 to the 11 Newton meter squared per kilogram squared, multiplied by the mass of the Earth, mass of the object, divided by r. Notice these are 1 over r's. These are no longer inverse square laws. This is an inverse, just an inverse. Okay, and that purely comes from having to integrate over 1 over r squared. Okay, remember, you can skip all that calculus business and just use this formula. Okay. Now, interesting question here. So let's go back to that idea. I want to throw something up into the air until it's gone. How much energy do I have to initially give it? I have to get some point in which the kinetic energy is actually greater than this escape energy. Right? What's my minimum? Minimum escape energy is when they're equal to each other. Really, for this to happen, K has to be greater than U escape. Right? I have to give it enough energy to overcome this. But for us to calculate my escape velocity, the amount of speed that I have to give something for it to disappear off the Earth, I can just use it as equal here. So the kinetic energy is half mv squared. Escape energy is this new expression we have here. Isolating for v squared, multiplying by 2 on both sides. M's cancel. The escape velocity does not depend on the object's mass. Escape velocity does not depend on object's mass. Crazy. Escape velocity is constant no matter what it is. Whatever planet it is, every planet has a constant escape velocity. That's awesome. Anyways, and there's even some like planetoids that have escape velocities of meters per second. Small little things like some of the tiny little moons of Pluto that only have, you know, radii of a couple kilometers, something like that. Meters per second. You can jump and never come back down. Anyways, so isolating for v, we get the square root of 2gm over re, and substituting that in, we get this number. So if I am able to jump at 11,000 meters a second, I will never come back down. Okay, if I supply a speed of 11,000 meters a second, I'm never gonna get back down. Just a quick homework problem here. This is my units of G, Newton meters squared per kilogram squared. Then I'm multiplying by kilograms, and I'm multiplying by dividing by meters. How the heck does this work out to meters per second? You guys show me that, okay? That's part of your homework. Show me that the units of that work out. All right? And let's just back up to the beginning. Remember at the very beginning I said that the potential energy, gravitational potential energy of the lab frame is mg delta H. And now I'm giving you this new scary expression, GMM 1 over r minus 1 over r2. Are these things equivalent? If delta H is small enough, if delta H does not change R1 and R2, if R1 and R2 is almost the same, because delta H, this delta H, which is going to be much, much, much smaller, right, than that delta H, one second, what am I saying here? Delta H is, right, R1 minus R2 is equal to my change in height, right? This is almost infinitesimally small. This is incredibly small, okay? Does that mean that this expression becomes that expression? This is the general one, but can I somehow show that this expression for the potential energy turns into this one? Now, this is not straightforward. You may have to play with something called a Taylor series. Maybe look that up. You may have to do a little bit of calculus. You may have to look at what are some approximations for 1 over r. Okay, so that's a homework problem. That's an advanced, challenged homework problem. Show me that, okay? If you can't do it, don't worry about it. Just do the homework problems, which are these ones, okay? 1 to 5 here. Calculate here. 1 to do these answers. These are the homework problems. Here's a good one. Number 2 asks us, if I go 100 kilometers above the surface of the Earth, and if I use one of my formulas, my new one I just gave you, or I use the old one, what's the difference? Oh look, it's only 2% different. So you're 2% wrong when you're only within 100 kilometers. Okay, so within that 100 kilometer radius of the Earth, we can just use MGH. All right. So this new expression really is for celestial objects, things that are much farther away than this. Right? We know that 100 kilometers, that's 10 to the 2 is much, much, much less than 10 to the 6. All right. So, so homework, we're asking you to figure out this guy here. Do the units work out? Do these problems, and then if you want to have some fun, Math fun. I love math. Show me if you can work. Show me if you can make this guy work out to be that one there. Okay, and we know we have an expression for g. We know that g is equal to m. What is it? You guys remember? Mass of the Earth, big G over radius of the Earth squared. Okay, we know this guy, so you can put that in there. See if you can figure it out. All right, good luck. Okay, so that's me from now on. Hope you guys are doing well, and talk to you later.